Okay, let us briefly recall where we were in the last class. We said that ask him to stop. Yeah. We said that when there is a periodic orbit like so in continuous time, and suppose you have placed a Poincare plane here, you would normally see a point, but supposing this orbit becomes unstable, which means the fixed point here becomes unstable, and not just any type of instability, it is that instability where the in the map where the eigenvalues are complex conjugate and their magnitude is just equal to 1. So, when that happens, on this you will find, if you blow it up, you will find that in the neighborhood of that you will get a outward spiraling orbit, while outside there will still be incoming spiraling orbit, as a result of which there would be a closed loop developed. A closed loop on the Poincare plane would mean that there is a torus in the whole continuous time. Okay. So, that is the picture that we have seen, and then we said, okay, now we forget about what is happening elsewhere, we keep it in the back of our mind, but let us concentrate on the Poincare section. And then, since on the Poincare section we will see this is a rotating orbit, this will be a, since the fixed point that is sitting inside has become unstable while the eigenvalues are complex conjugate, there should be a rotational motion, and the rotational motion will give rise to a turning this way. So, we said that suppose we consider the rotation on a circle, topological circle, which is no different topologically from any closed loop, and then we define the angle and said that let us define theta n plus 1 is equal to a function of theta n, let that be the equation. So, we defined a map, 1D map, that represents the angular rotation or angle in any particular iterates measured from any datum. So, that is where we were, and we had used for that purpose a specific map given by theta n plus 1 is equal to theta n plus omega minus k by twice pi sin twice pi theta n, and then you have to take mod 1. Is it visible? Yes. So, this is the sine circle map that we had taken. Do you have any question? So, we had taken the sine circle map, and then we had gone ahead with this argument that if this is the representation of the dynamics as it turns, then we can identify very easily the situation when there would be a mode locking, 0 to 1 mode locking. We can easily identify the 1 to 1 mode locking, right. What would represent the 0 to 1 mode locking? The condition where it does not at all rotate in the small circle. So, it goes around the big circle and comes back to the same point, which means nothing but a period 1 fixed point. Okay. So, to find out the condition, we had set this equal to theta star, this equal to theta star, this equal to theta star, solved it, and we obtained the condition. Likewise, what would be the condition for 1 to 1? 1 to 1 mode locking would mean physically that while it goes around the big circle once, it also goes around the small circle exactly once. Okay. Going around the small circle exactly once means addition of 1 in this case, because it is normalized to 1. So, in order to obtain that condition, we had simply put theta plus 1 and we had solved it and we got the condition. simple. But that way we convinced ourselves that there would be two parameter ranges. Here there are two parameters, the omega is a parameter and k is another parameter. There would be two parameter ranges in which you would have a 0 to 1 mode locking and 1 to 1 mode locking. We had more or less come up to this stage in the last class, right. So, do you exactly recall what the ranges were? So, 0 to 1 mode locking condition was all right, and 1 to 1 mode locking condition was right. So, notice that as k goes to 0, because k is a parameter and we have already understood that k is a non-linearity parameter. If k is set to 0, it is linear map. Notice if k is set to 0, it is a linear map, and then omega becomes the frequency ratio parameter, and k is a non-linearity, it brings in the non-linearity. So, if k is 0, then you would notice that there is no range. If k is equal to 0, no range, but as k is increased, you get some range, and if k is equal to 0, you get a lot of range. Okay. No, k is equal to 1, k is equal to 1, you get some range for this one and some range for this one. And it is customary to visualize this as a graph in the omega versus k plane, in which how would this condition look? This is 0, this is 1, and here it is 0 to say here it is 1. 1 I will draw a dashed line. So, this would be nothing but a straight line condition that goes up. For k is equal to 0, the range of omega for which this happens is 0. For k is equal to 1, it is 1 by twice pi. So, you would get a range like this. Fine.
So why are we limiting k to 1 up to 1?
No, we are not limiting. We are only now studying what happens between 0 to 1. It is not really limited to 1. We will see what happens if it goes beyond 1. Then here also this is a range that is limited to 1, but it starts from 1 minus k by twice pi, and so here is also a linear range that goes like this. So, this is the range in which you will see 0 to 1 locking, and this is the range where you will see 1 to 1 locking. Good. Now, the question is that in between these two, will there be other mode locked conditions? Now, other mode locked conditions means what? Means, as you can see, that in case of this kind of a map, the mode locked condition is represented by periodic orbits. If it is periodic, then it comes back to the same state after some time, which is nothing but a mode locked condition, right. So, by the same procedure that we have already learnt, we can find out the range of parameters for which it becomes period 2, for example. If you try to do that yourself, this will give you some trouble, because you will land up in a transcendental equation. So, that needs to be solved numerically. If you do so, then you will find that here also there is a range that goes like this. here is a 1 to 2. Let us try to figure out how the 1 to 2 situation looks in the graph. Here is your theta n, here is your theta n plus 1 graph of the map. Here is the 45-degree line. So, it would be something like this, and then from here it will come back here and it will start like this. So, you can visualize a orbit something like this, say here to here. No, the drawing is not correct. I'll draw again. So, supposing it goes here, it comes here, so it has to come back somewhere here. So, an orbit can be something like this. If it is like this, that means one iterate falls in this chunk and another iterate falls in this chunk. Falling in this chunk means it is actually gone up like this, not here. So, here it is continuation of that line, and it has come down here because it is mod 1, right. So, actually the graph is going up like this, but since you are taking a mod 1, it starts all over again here. As a result, if there is a iterate falling here, it means that it goes around it one circle, right. Is that clear? So, this orbit would mean that it goes around the small circle once, and period 2 means it goes around the big circle twice. So, it is a 1 to 2 mode locked orbit. Clear? Why it is mode 1 to 2? Similarly, you will be able to visualize a 1 to 3 mode locked orbit something like this. This was creating problem, bad paper. Drawing this is difficult, so I will just show you the graph from the book. Can you see? Yeah. Can you see this graph? So, this is the period 3 orbit, fine, and in the period 3 orbit, I mean they have shown it starting from some initial condition with some iteration, that means the cobweb diagram. Finally, it converges onto the period 3 orbit. What would be the winding number for this one? Looking at this, can you figure out? Not difficult at all, because there are 2 iterates in this chunk, which means that it goes around the small circle twice, while there are in total 3 points. Therefore, it goes around the big circle thrice. So, it is 2 by 3 mode locking window. Okay. Now, for these 2 situations, one was this situation and the other was that situation. For these both, you can plot theta n plus 2 versus theta n. Can you see, or is it too faint? I will draw again. I will draw on the paper. In one case, I will have to draw theta n plus 2 versus theta n, the way we did for the logistic map, in order to understand the character of the period 2 orbit, and the other case we will need to do 3 plus. Okay. In this case, there would be this kind of behavior. So, as a result of which there would be few fixed points around it. In this case, there would be more number of these things, and it is not difficult to see that the more you increase this number, that means which iterate I am talking about, the more would be these oscillations. Is it difficult to visualize that? No, because we know in case of the logistic map, we have seen that in case of period 2 there would be 2 of these, in case of period 3 there would be many more of these. So, as you go on increasing, there will be more number of oscillations. Same thing will happen here. The point that I am trying to make is that therefore, the more the periodicity I am investigating, we will have to take n plus that many, the more there would be those number of oscillations. Now, look at the character of the look at the character of this. What does omega do? Imagine I am drawing the graph of this, and what is the role of omega? It is just moving it vertically. Okay, it is just moving it vertically. As a result, if you move this vertically, the intersections will exist only for a certain range. Okay, I am trying to give you a sort of intuitive argument that you can appreciate. Mathematically, everything can be worked out algebraically, but very long calculations will be necessary. So, I am trying to give you an intuitive argument. There would be oscillations in this graph. Now, the more this periodicity, the more will be the oscillations. As a result, as the omega is increased, this will be moved, and naturally, the higher the oscillations, the smaller will be the range of omega for which this orbit this graph will intersect the 45-degree line. That is exactly why when you plot, you find that as you increase let's put it this way. First let us understand the argument for k. We find that these broaden as you go for higher values of k. What actually happens for higher values of k? If k is 0, there is no oscillation at all, they are straight lines. If you introduce k, it becomes slightly like this. The more it increases, it becomes larger oscillations. As a result, the intersection will exist for a larger range of omega as this goes up and down. Fine. That is exactly why for larger values of k, we have a larger range of omega for which these are stable. Okay. Is that argument convincing? Fine. Now, we will get into the interesting part of it, if these arguments are understood. So, the larger the value of k, the larger will be the range of omega for which we will get the periodic mode locking windows. Second point is that the higher the periodicity, the narrower will be the range in which they will occur. Now, the periodicity, you will notice that if the periodicity is p by q, if the winding number is p by q, then periodicity is this q, the denominator, right? Periodicity is q, the denominator. As a result, you would immediately conclude that the larger the denominator, the smaller will be the range of the parameter for which it will occur. Okay. At this stage, number theory comes in because here we are talking about rational ratios starting from 0 to 1, or I will write it this way, 0 to 1, basically 0, and ending it 1 to 1. In between these two, how many rational ratios are there? Infinite. As a result, it is not difficult to see that within these two ranges, here is the range of occurrence of 0 to 1 mode locked window, here is the range of occurrence for 1 to 1, in between there should be all these infinite period mode locking windows. Okay. We also conclude that the higher the periodicity, that means the higher the denominator, the narrower will be the range. A nice way of visualizing that is if we plot omega versus the winding number. It must start with 0 and it must end with 1. So, it goes from 0 to 1. Now, you are using omega as a parameter. Say you are setting some value and you are slicing through this, right? You are slicing through this. what you will see? You will see all these ranges in which there would be mode locked windows. As a result, this graph looks like this, difficult to draw, extremely difficult to draw. There would be a range here, 1 to 2 mode locked, there will be a range here, there will be a range here, there will be a range here. So, I will not draw it with continuous line. It will be a graph like this. You will get a graph like this. What is the speciality of this graph? Each of these horizontal lines represent the parameter range for which a periodic orbit occurs, a mode locked window, right. And since if I ask you how many of these mode locked windows are there, your answer would be infinite, because there are infinite number of rational ratios between 0 and 1. Okay. So, if you imagine that this is a staircase and an ant starts from here trying to climb up to 1, how many steps does he have to climb? Infinite. He says, okay, no, I do not want to get up to that level, I only want to get up to that level. How many steps? Still infinite. No, I do not want to get up to that level, I only want to get here. How many steps? Still infinite. So, you see, in order to go from any place to any place, he has to climb infinite number of steps. He actually cannot climb. That is why this typical structure is called devil's staircase structure. This is called devil's staircase structure because you never can climb such a staircase, but it is a staircase. That follows from number theory. Is that clear? The concept of devil's staircase. How will you actually calculate this? Omega is a parameter. For every value of omega, you will actually have to calculate the value of omega. Every value of omega, you will have to calculate W. How will you calculate W? The average number of turnings. So, you will have to take Fn of theta minus theta, you have to take limit n tends to infinity. Okay. So, this way you have to calculate the W, the winding number, and then you have to plot this graph. It is possible to plot. I mean, the ant cannot climb, that does not mean you cannot plot. It is possible to plot this graph. Of course, you will be able to calculate these to a finite precision of the computer, but nevertheless, it is possible to plot these graphs. Another very interesting thing follows from number theory. See, there is a range with 0 winding number, there is a range for 1 winding number. No, I'll write somewhere else. Suppose there is a range, suppose there are 2 rational ratios I am talking about. Now, forget about dynamics, just consider number, 2 rational ratios, P by Q and P dashed by Q dashed. Suppose this is 2 by 3, this is 4 by 7, and suppose these are not, these are brought down to the minimum level. That means, we are not talking about 4 by 6. If it is 4 by 6, we will talk about 2 by 3. So, suppose there are two rational ratios, then number theory says, there is a theorem that says that the rational ratio that occurs between them with the smallest denominator is okay. This does not follow from dynamics, it follows from number theory, was proved pretty long back. It is a number theory proof, but that immediately becomes applicable here. Why? Because here we are talking about rational ratios, and we are interested in mostly how big is the parameter range over which it will a specific ratio will occur. For example, suppose I am trying to find out which is the mode locked window that will occur between this and that. Obviously, for practical purposes, we will be talking about the window that is largest. Essentially, we are talking about this. Then number theory says that that can be simply found by p plus p dash by q plus q dash. Why? Because the number theory says that this denominator is the minimum. Okay. So, between this ratio and that ratio, if I ask you that which is the rational ratio that has the minimum denominator, then this is the rational ratio. And we have already said that the ratios with a small denominator will occur for a larger parameter range, and therefore, you can conclude that this particular ratio will occur for the largest possible parameter range between these two. Okay. Good. Now we can start from say 0 as a ratio and 1 as a ratio and try to build what will happen in between. Obviously, between 0 and 1, 0 means 0 by 0 and this is 0 by 1 and this is 1 by 1. In between there should be, this is p by q, this is p dash by q dash, there should be the largest ratio of 1 by 2, these two added 1, these two added 2. So, in between there should be 1 by 2. In between these two, what ratio do you expect? 1 by 3, yes. In between these two, what ratio do you expect? 2 by 3. In between these two, what ratio do you expect? 2 by 5, yes. In between these two, what ratio do you expect? 3 by 5. In between these two, you can easily construct. Can you see that it goes up? And as it goes up, you have the ratios with a larger denominator, and smaller denominator ranges occur to the base of this tree. Okay. What will be here? Quick. 1/4. What will be in between these two? 3 by 9, 1/3, right? 2 plus 1, 3, 4 plus 5, 9, 3 by 9 is nothing but 1/3, and so on and so forth. You will be able to build up the tree yourself, and actually that is what happens in dynamics. If you see a bifurcation diagram of this system, then you will be able to identify exactly these ratios as the mode locked windows occurring between them. This tree is called the Faraday tree. This tree is called the Faraday tree. Okay. So, now we can do some filling up of this. In between these two, what do you expect? In between 0 and 1, you expect a 1:2 ratio. It happened. In between these two, you expect which ratio? 1 by 3. So, that should be something like this. It should be widen up like this. In between these two, what will you see? This is 1, 2, 3, 1:3, right? 1 by 4, yes. So, there will be a range like this. Here will be a range like this. Here will be a range like this. of various widths depending on the denominator. Now, these ranges, these geometrical structures, after the person who invented them are called the, in nonlinear dynamics, people are very imaginative, they give all sorts of funny names. So it is named after his tongue. So these things are the Arnold tongues. He was a mathematician in the 1960s who noticed this structure. Okay, fine. So you have these nice Arnold structures. What are there in between? In between, is there any gap in between? Yes, there are gaps in between, because these ranges broaden. Suppose they almost fill the top part, then obviously they don't fill the bottom part because they are broadening. So if you take a slice here, in between there will be ranges where there is no mode locking. Then what is there? Irrational ratios, and the irrational ratios are what? Quasi-periodic behavior. So in between you have the quasi-periodic windows in these gaps, and it is easy to see that the ranges in which quasi-periodicity occurs will be large for k close to 0, and the ranges in which the mode locked windows occur, they will be large as k goes to 1. I will get back to some more concepts of number theory a little later. By the way, have you heard of Fibonacci series? Where? C programming. Okay, they're okay, good programmable things, all right.
Sir, can you please explain the theorem in P by Q and P dash by Q dash?
Yeah, it says that between the numbers 0 and 1, there would be an infinite number of rational ratios. But then the question naturally comes, is there any ordering, or they occur in any way? Mathematicians showed that no, they occur in some specific ordering sequence, and they showed that if you have in between somewhere a ratio p by q, and somewhere here a ratio p dash by q dashed, then in between there must be the ratio p plus p dashed by q plus q dashed. And not only that, this particular ratio has the lowest denominator in between these two. In between these two there will be infinite number of rational ratios, but all of them will have a larger denominator than this one.
So if we take 1 by 5 and 5 by 9.
So take 1 by 5 and 5 by 9. In between you will have 6 by
14.
so cut off.
But in between there is half.
Hmm?
In between there is half. So the number half. Half. 5 by 9 is
In between the number half also occurs, is it? No, not just anywhere. Actually, this has to build on the Ferret tree concept, then only you will get it. That means here you have these ratios. In between the maximum is this one, in between the maximum is this one, in between the maximum is this one, and so on and so forth. That way you have to build on.
So, sir, it is valid for the fractions which occur on the Ferret tree.
Yeah. It will.
Actually, anything which they can build it up.
No, ultimately all the fractions will occur somewhere on the Ferret tree. Somewhere. but building up is this way, which means that in between these two the maximum ratio is half, in between these two the maximum ratio is this, in between these two the maximum ratio is this, and so on and so forth.
So we can take between any two.
Any two of the members?
No, it has to build this way.
So
It
we
is
cannot take between 1/4 and 3/5 in that case. Can we?
oh, this will not be allowed then. Yeah. 1 by 4, 1 by 3 you can take, yes. Between the consecutive ones you can take.
So between 1/4 and 3/5 we cannot.
1/4 and
3/5 and 3/5.
no, between consecutive ones you can take like this. Between consecutive ones you can build up like that. P by Q by Q dash P dash by Q is
These fractions which are coming in this direction.
no, all the fractions will ultimately occur in this direction.
Fractions will occur.
All the fractions will occur in this direction because the ferrity actually contains an infinite number of fractions. Okay, your point is correct. You cannot just join anything. You're right. Okay, before I go into the Fibonacci sequence and all that, I'll have to talk about something. All this is fine, but what actually happened on the Poincare section? I said that there was a fixed point here, which had become unstable. Even though that became unstable, and now there is a closed loop around it, that fellow is still there. As an unstable periodic orbit, that fellow is still there. But as we said, that supposing a periodic orbit has developed, which has one point here, another point here, and the third point here. The question then is, what makes the loop? I can find 3 points. On what basis do I say that there is still a loop? On what basis do I say that it is a movement on a torus? Obviously, a valid point. I have to have some construction that shows how these parts are constructed. Now, whenever there is a birth of one of these periodic windows, all periodic windows are born through saddle node bifurcations, and there is no exception here. Here also there is a saddle node bifurcation that happens, through which these are born. That means, when this periodic window, this period 3 is born, there is also a saddle that is born. Suppose the saddles are here. That means, when they are born, this point and that point was very close, this point and that point was very close, when this point and that point was very close, as you change the parameter, then they move apart. If these are saddles, and if these are nodes, then we can draw the stable and unstable manifolds. So, the saddles will have the stable and the unstable manifolds like this. These would be the stable manifolds, and these would be the unstable manifolds. Sorry. So, anything that is inside, because of the action of these stable manifolds, goes outward to this loop. Anything that is outside, because of the action of these stable manifolds, go into this loop. But then these are the stable points. So, from here, this is wrong. From here it would converge onto this. From here also it would converge onto this. From here it would converge onto this. From here also it would converge onto this, like so. And on this there would also be stable manifold, because these are stable equilibrium points. If you individually take this point and obtain the eigenvectors, there would be 2 directions. So, here also there will be this, here also there will be this. These are all incoming then. because these are stable. All right. What happens to these guys as if you extrapolate them further? They must all converge onto this point or diverge from this point. But this point is a spiraling orbit, right? This point, if you take a closed neighborhood and obtain the Jacobian, this will lead to spiraling orbit, which means that it would be a spiraling thing and so on and so forth. So it is actually like this. So here it is a spiraling orbit, but as it diverges, they become the stable manifolds that are shown here. I would better draw some of these with different colors. These are, I am drawing with black then, these are the stable manifolds of the saddles, and these are the saddles. This is a saddle. So and this is another saddle. Now do you see who is creating the closed loop? The closed loop is actually formed by the unstable manifolds of the saddle fixed points and the stable manifolds of the nodes. The unstable manifolds go outwards and converge onto the stable manifold of the nodes, so on and so forth, and that is what creates the closed loop. So that is the geometric process of creation of this closed loop. Clear? So this closed loop is actually there. It is a geometrical construct not out of our minds, it is there. So even if I can identify only 3 points, still we can say with confidence that it is a mode locked window, not just any type of period 3 window. We have already seen that there are period 3 windows in, say, the logistic map. One way of looking at it is that if you see that means in the logistic map there is a period 3 window, fine. That is also a Poincare section of some kind of a continuous time system. I take the data, do some kind of data acquisition and do a FFT. What will you see? We will not see 2 sharp lines, but here you will see 2 sharp lines, meaning that it is still the orbit on a torus. Okay. And geometrically what is happening is that on the Poincare section you will have this structure. Fine. Okay. Now let us see what creates chaos. In order to understand that properly, what created chaos in case of the logistic map? See, in order to have chaos, you have to have sensitive dependence on initial condition. What causes sensitive dependence on initial condition in the logistic map? See, logistic map, let us draw, it was like so, xn versus xn plus 1. What created the sensitive dependence? Notice, if you take an initial condition somewhere between 0 and half, this range is stretched to the range 0 to 1, right. So 0 to half range is stretched to 0 to 1, and half to 1 range is folded. So actually it goes, this range goes to this. So and this range is here and this range is there. So it actually folds. Okay. So you have the stretching as well as the folding. Okay. Stretching and folding are therefore a essential consideration for creation of the chaos, but that's only if you have a stretching and folding, it doesn't necessarily guarantee chaos, because you know that if mu is say something like 3.1, it is not chaotic, it is some high periodic orbit, say period 4, period 8, something like that. But in that situation also there is stretching and folding. But what I am meaning is that the stretching and folding is a necessary condition for creation of chaos. Now, let us look at it from another angle. What causes the stretching and folding? If you see this, for every value of x n plus 1 there are two values of x n. It is not invertible, okay, not invertible, you cannot invert it. If you have x n plus 1 is equal to function of x n, that does not allow you to say x n is equal to another function of x n plus 1, right. Geometrically what is there? If you have the x n plus 1 given, that could have come from two values of x n, either here or here. As a result, if you want to take the inverse map, you do not know which point to take. That is the non-invertibility condition, and that is also at the base of this stretching and folding. Now, look at the sine circle map, its behavior. We have already shown how it looks. It has it looks like this if k is equal to 0. It looks like this if you have some value of k, and it will look like for k larger than 1. Somebody was asking why limit k to 1. If you increase k to a value larger than 1, so you have this situation, so that for a value of x n plus 1 there are many values of x n that is possible. The map becomes non-invertible. It is also easy to see that under that condition there is a stretching and folding.
The map is already non-invertible. You are taking on the part. But if you extend that,
If you extend that, what was the behavior? See, if you extend without taking down, if you extend that, what will happen? It was actually like this, and then it becomes like this.
no, I'm not trying to say that. I'm trying to say that you are taking only a part of the map, isn't it? It's
No. It is between 0 and 1. I am not taking a part of the map. Map is defined between 0 and 1. Because of the mod 1 condition, I am taking the mod 1, thereby I am limiting to 0, 1, 1. So, I am not taking a part of the map. This is the whole map, and the whole map, so long as these lines, see, it was like this, it was like this, it was like this, and finally it becomes like this. When it becomes like this, there is a non-invertibility condition that has come in, and that happens when k is 1. That is why, so long as we were considering the situation where k is less than 1, you have essentially invertible maps, and that is why for k less than 1 you do not see chaos, because the condition is not satisfied, the stretching and folding condition is not satisfied. But the moment it becomes like this, the stretching and folding condition is satisfied, and therefore the condition is now ripe for generation of chaos.
So you are saying that the non-invertibility is necessary for chaos?
No, I am not saying that. I am saying stretching and folding is necessary for chaos, and non-invertibility is a condition that causes stretching and folding.
So, but in sir, Heron map, we have seen chaos, but it is invertible.
Doesn't really matter. If something is non-invertible, then you have stretching and folding. The reverse is not true. Okay. Fine. So we conclude that if you have, where is that diagram we had? Yes, here. If you stretch k further, up there we expect chaotic behavior. But we have also seen that in this part there will be more of quasi-periodic behavior, in this part there will be more of periodic behavior, more of periodic behavior. Therefore, as it goes up, see, even though here you can expect a more of periodic behavior, the quasi-periodic behaviors are still there. It is not that they are non-existent, only their ranges become very narrow. It is possible to imagine that I am keeping omega constant and I am varying k through a line which goes all the way through quasi-periodicity zone. It is possible to imagine that. It is also possible to imagine that I am varying it through a line that goes through a periodic zone. So, in these two cases we need to consider this situation. In one case it is the transition from periodicity to chaos, in the other situation it is a transition from quasi-periodicity to chaos. We need to consider both these situations. Okay. We will take this issue up mainly in the next class. These transitions, different ways of transitions, we will take up in the next class. But before that, since you have said that you have some background on Fibonacci numbers, all of you have? Is there anybody who does? Good. So, you know that the Fibonacci series is essentially 0, 1, add them, so on and so forth. And what is the Fibonacci ratio? Now, Fibonacci ratio is, or golden ratio it is sometimes called, is if you go on making ratios of the subsequent numbers. That means, the first ratio is then and so on and so forth. This series actually converges onto a ratio. This series actually converges onto a ratio, and that ratio has been found to be very important in nature in various ways. When saplings grow, the distance in which the leaves sprout, if you measure the distances, you will find that they follow this Fibonacci ratio. There are those shells in which there is a winding, those windings follow the Fibonacci ratio. Even our aesthetics follow the Fibonacci ratio. Postcards are made in Fibonacci ratios. So, there are various ways in which the Fibonacci ratio becomes very important. For example, this I do not have to measure. If it looks good to our eyes, this ratio, this rectangle, if it looks good to our eye, the ratio is harmonious. Immediately you can say with confidence that the ratio must be Fibonacci ratio. Then go ahead and measure it. You will find that it is the Fibonacci ratio. So, that has various ways in which the Fibonacci ratio appears in natural sciences. And in the next class we will see how it appears in dynamics also. In very interesting way it appears in dynamics also. Okay, that is all for today.